Hi, everyone. I wanted to welcome all of you to the first ever Target Test Prep GMAT Math webinar. So we're very excited that all of you could show up tonight. This is going to be the first webinar of hopefully an ongoing series. Scott and I haven't really talked about when it's going to end, so maybe for a very, very long time that we'll be hosting on Tuesday nights. For those of you who don't know Scott or I am the head GMAT instructor with Target Test Prep as well as the COO, and Scott, of course, is the founder and CEO. Both Scott and I, we have been GMAT instructors throughout the duration of Target Test Prep, 7 years for me, even more for Scott, and I would like to think that we both probably combined tutored over about 20,000 hours of GMAT tutoring, if any of you can imagine that. So there's a lot of knowledge that we can give you guys here in these webinars. Certainly, don't hesitate to ask questions. I'll be kind of standing by if you have questions as Scott's doing some teaching. And of course, we'll leave about 15 to 20 minutes at the end of the webinar so you guys can ask questions either about the content that we're covering tonight or even just general GMAT questions that you might have. And furthermore, you can always reach out to us even after these webinars via email or phone. We'd be more than happy to chat with everyone. Finally, tonight we're going to be talking about quadratic equations, a lot of the quadratic identities. Scott's going to be going through a lot of different questions. Just so all of you know, these are questions original from our curriculum. Some of you here know about our curriculum. It's something we'll discuss more about, but we're really excited about it. We spent many, many years creating it, so we feel like you guys can all benefit greatly from it. And the best part is everyone who attended tonight, we will follow up with a discount code for anyone who wants to purchase the 6-month subscription. And if you're taking the GMAT really soon, feel free to reach out. And there's some shorter-term ways that you could get our curriculum. Lastly, just keep your mics on mute as we're kind of going through things. If you do have questions, just direct them to me through the chat box. And that's about it. So Scott, I'll leave it to you, and you can take it away.
Thanks, Jeff. Hey, guys. Thanks, everyone, for coming. Bear with me a little bit. I just had a rough cold the last week, so my voice is a little bit off. But I appreciate you guys coming here this evening and hanging out with us for the hour. So what we wanted to do is, I recognize a lot of the names here, and I know most of you know a little bit, or at least maybe even a lot about the GMAT. So this is going to be a high-impact webinar. We're not going to go over any of the basics. What we're going to do is we're going to kind of focus on the theme of pattern recognition. And pattern recognition is something that's really important for all standardized tests. The GMAT in particular, to be able to learn something, call it A, and then see something B at a later date and say, B looks kind of like A, and maybe if I manipulate B enough, it actually is A. And tonight, what we're going to do is we're going to use quadratic equations to help us with this larger strategy of being able to recognize patterns. Now, for the GMAT, many of you know there are 3 really important quadratic identities that we have to know. And we're going to talk about these just a little bit because they're pretty basic. And then we're going to jump right in and we're going to do a bunch of problems during which you're going to solve these problems. I'll give you guys about 2.5 or 3 minutes per problem, and then we'll discuss the answers. So we'll try and go not too fast, but not too slow, give you guys enough time to work the problem out on your own and take some good notes. And as Jeff said at the end, you can ask any questions you have. So the first quadratic identity is something that looks like this. We have x plus y, and the whole thing is squared. And most of you know at this point right away, you say, business as usual. This is the same thing as x plus y times x plus y. And if you continue doing the math, you would all say, this is x squared plus 2xy plus y squared. Pretty basic. Now, why is this called an identity? It's called an identity because these three forms, these three identities, are exactly the same anywhere in the world of math. X plus y squared is the same thing as this, which is the same thing as this. Okay? The second quadratic identity you must know is very similar. It's x minus y squared, and most of you see that this is the same thing as x minus y times x minus y, which of course, if you keep going, is x squared minus 2xy plus y squared. Okay, again, it's called an identity because this is always the same as this, which is always the same as this, anywhere in the universe, as far as we know. Okay, so in the GMAT, it will be true. The third one is of particular importance, and if you've ever been my student, you know I harp on this all the time. X squared minus y squared. Now, this is called the difference of squares. X squared minus y squared always can be simplified to x minus y times x plus y. Okay, give me a minute to write that down. Okay, so then why is this important? How do we use these to see patterns? Well, here's what I want you to think about. And you can apply this to quadratics, you can apply this to exponents, you can apply this to many types of questions on the GMAT. It's a pretty good strategy that if you see something in this form, so x squared minus y squared, there's a really good chance to solve the problem. You need to re-express it in this form. Okay? If you see something in this form, there's a really good chance you either need to re-express that thing into this form or to this form, for example. Or, for example, if you saw something in this form, there's a really good chance to solve the question. You need to arrange it into this form or into this form. And that's the pattern recognition, right? Being able to see structures within this mess of data, meaningful structures within this mess of data. And I guess if you think about it, that's a pretty important skill to have going on to business school or going on into your life after business school. Okay? So what I would like for you to do is to keep these three quadratic identities in mind. And what we're going to do is we're going to jump right into solving some problems. And the tip I'll give you is you will use one, some, or all of these quadratic identities to help you solve these problems. Now, as I said, what I'm going to do is I'm going to give you about 2.5 or 3 minutes to solve them, and then I'll give you a solution. Now remember, when you start these, so if you're starting this problem, if you're about ready to square 555, stop. You know you can't do it. You'll never do it, right? With an Excel sheet, it would be difficult. Find a creative way to solve all of these problems, and we'll start the time now. Yeah, guys, and you can put your answer in the chat box when you get it. And I think the key is to make sure that everyone can see the answer. Thanks, Kristen. Okay, guys, that was about 2 minutes. Now, one of the things, this is sort of as a side note, when you're studying for the test, it's really important once you have a base foundation of knowledge to time yourself, because it's uncanny how fast 2 minutes goes when you look at the time when you're trying to do something. So what I want to do is I want to give you some insight how I would solve this. I would look at this and I'd say to myself, there's no way I can do this math. I would make so many mistakes in the process of even subtracting these numbers that it wouldn't be worth it. But if I can use my pattern recognition, what I can see is that the numerator is in the form of the difference of squares. Remember, the difference of squares says that anytime we have something in the form of x squared minus y squared, this is always the same thing as x minus y times x plus y. And lo and behold, this is going to help us here tremendously. But I first want to make sure you guys all see this. Look at the numerator. You have something squared minus something else squared. Well, that's difference of squares, and that's good for us on the test. Okay, so what we can do is let's re-express the numerator. We'll say the numerator can be written as 555 plus 55 times 555 minus 55, and all I did there is I just made it in the form of x minus y times x plus y, right? With the 555 being the x and the 55 being the y, okay? And of course, that's still all over 500. Now notice what happens here. Obviously, 555 minus 55 is just 500, so we can cross these guys off from our fraction, and we're simply left with 555 plus 55, which of course is going to sum to 610, which is answer choice E. Okay? So the big thing I want you guys to see is, it may be a simple problem for some of you, it may be really difficult for some of you. It doesn't matter. What matters is I want you to see there are creative solutions for every problem on the GMAT. Okay? I'll give you guys a minute to just take any notes, and I'm going to get our next problem ready. And if you have any questions, of course, you can ask at the end, just to keep the meeting fluid. All right, guys, here's the next one. Let's take about 2 minutes and see if we can solve this. Again, look for some patterns. Look for some structures you recognize. Let's take it away. That's right, guys. If you have any questions, you can address them to Jeff in the chat as we're going. If you have a burning question that you want to get answered before the end of the webinar, just direct it to Jeff in the chat, and he'll do a wonderful job helping you. Okay, guys, again, that's about 2 minutes. So let me show you how I would think about this problem, okay? You know, I'd say to myself, there's no equation here, so there's nothing I can do to the other side of the equation. Whatever work I have to do within the fraction. It's just an expression, right? So I look at the numerator, and it's tough to see, but if you look closely, it's again in the form of the difference of squares. Because if you look carefully, and guys, the denominator is a little bit of a tip-off here. If you look closely, you can see that x to the 100 can be re-expressed as x to the 50 squared, right? Because we know that power to a power rule tells us that when we have x to the a raised to the b, well, that's the same thing as x to the a times b. So if you think about it, x to the 50 to the square is the same thing as x to the 100. Right? So again, it's all pattern recognition. So I'm re-expressing the numerator as the difference of squares, right? Now, we have difference of squares because we have the x to the 50, right, squared minus y to the 50 squared. And once we've done that, we have a pretty good foothold into the problem because look what we can do. Let me get rid of this guy. This guy up here out of the way. Look what we can do. We can re-express the numerator and say, well, this is the same thing as x to the 50 minus y to the 50 times x to the 50 plus y to the 50. And I told you that the denominator was a little bit of a tip-off because lo and behold, there's your cancelable item there, right? The x to the 50 minus y to the 50s cancel. Because if you think about it in this question, the denominator had to go away somehow, right? Some way. And we're simply left with x to the 50 plus y to the 50. Okay, so again, all we did there is we just used the difference of squares to make this meaningful for us. Okay, take a minute, take that guy down. And we're going to make it a little bit difficult with the next couple problems. These two were a little bit on the basic side. Okay, guys, give this one a whirl. So we'll integrate a little bit of number properties into this idea of critical quadratics. Start the timer now. Okay, guys, that was about 2 minutes. I know it goes by really quickly. So remember, on the GMAT, And in life, simplicity always trumps complexity. Complexity is a disaster. You want to make things simple. So look, if you're looking at this and you're saying, well, we need to know, which of these guys, it's a multiple of which of the following except. Well, I don't know. When I look at 3 to the 10th minus 2 to the 10th, I have no concept of what these numbers are. It's too difficult. They're too big. Then you have to subtract them. It's too esoteric for me. So what we have to do is simplify this. Strive for simplicity. Okay? So what we can do, again, guys, I think some of you are probably starting to catch on here, is we can re-express this. Well, watch this. 3 to the 10th is the same thing as 3 to the 5th squared, right? Power to a power. And 2 to the 10th is the same thing as 2 to the 5th squared. Okay, once again, we have something squared minus something squared, so we have to say, aha, there's the difference of squares. We're really harping on this tonight. It's important you guys develop the ability to see this. Okay, so then we can re-express this. We can say, well, this is 3 to the 5th minus 2 to the 5th multiplied by 3 to the 5th plus 2 to the 5th. And when students start getting good at these, I don't want to call them sophisticated because everything I'm showing you is really simple, but when students start seeing these clever ways of doing things, they say, well, when do I just break down and do the math? And the best advice I have is whenever you're able to. So for example, through your time studying, you should probably know what 3 to the 5th is off the top of your head because it shows up a lot, right? So 3 to the 5th is 243. 2 to the 5th is obviously 32. And then we have 243 plus 32. And that was a step you could do in your head. So you use the creativity to get to the point where the pen and paper can take over, so to speak, right? So 243 minus 32 is 211. 243 plus 32 is what? 275, right? So now we're back to a really basic skill, right? We did some pretty creative work here, and once we're at 211 times 275, we're really down to basic divisibility, prime factorization crap, right? Because we want to know, this is a multiple of which of the following except what, right? Well, 211, guys, it's really important to memorize your divisibility rules, but if you memorize those, you'll quickly see that 211 is not going to be broken down any further, but 275 is the same thing as 5 multiplied by 5 multiplied by 11. So at the end of the day, this ugly number, 3 to the 10th minus 2 to the 10th, is the same thing as this really simple number that you probably worked with in, 3rd or 4th or 5th grade, something really easy for you. Okay, so now that we understand the deep component of the number, 211 times 5 times 5 times 11, then we can look up top and figure out which one is it not a multiple of. Well, remember, what we have is a multiple divided by its factor will produce an integer, right? For example, y is 8 divided by 2, not to get off track, but y is 8 divided by 2, an integer. Well, 8 is a multiple of 2. 2 is a factor of 4, which is why we get a clean division. Okay, so if this number here in the red box is going to be a multiple of one of those numbers or some of those numbers, it's going to be those numbers are going to have to divide into it, right? Okay, they're going to have to divide into it. Well, obviously 5 will divide into it because there's at least one 5. 25 will divide into it because there's at least 2 5s. 55 will divide into it, right? Because in this number there's a 5 and there's an 11. So 55 will divide into it. And 211 will definitely divide into it. But try as you may, you'll never be able to get 75 to divide into that number. Okay? And, you know, for some of you who have been at this for a while, this may seem really easy, and that's a good thing. You're on the right track. If you're just starting off, this may seem like a lot going on, but I promise you, if you keep at it, it will become very simple for you. Again, notice we found a creative way to solve a difficult problem. And just to give you a little more advice, guys, the students I see who don't do so well, this is a generality, of course there's other variables on the test, they tend to not work hard enough on finding the simplicity within the complexity. They tend to make things more complex rather than more simple. So always look for patterns, look to make things more simple. Okay, very good. So this problem is really interesting that we're about to do because as with all math, there's a million ways to solve it. There's a 2-hour method, there's a 10-minute method, there's a 3-minute method, and then there's a really quick, efficient, savvy method. And I want to show this to you guys so that when you go out, when you leave tonight, you practice. I don't want you to think that quadratics only exist in algebra. They permeate many aspects of the test. So why don't we start the time now and give this a whirl. And you can put your answer in when you get it. All right, guys, that's 2 minutes. I say this a lot, but it's shocking to me how fast the time goes by when especially when you're working on a problem. So check this out. So a regular bathroom tile has a diagonal of 1,000 millimeters, 100 millimeters rather. So what we'll do is we'll draw this out, and this guy here is 100. And we know it has a perimeter of 280 millimeters. Well, got to know the formula for the perimeter, right? We know that that's 2 times the length plus 2 times the width. So what I'd like to do is just write out as much basic stuff as I can that comes right from the STEM before I try and do any heavy lifting. And right away, this should be a pretty obvious move here, guys. You can see that each of these terms is divisible by 2. So I'll divide the entire equation by 2 to get the length plus the width is equal to 140. And that seems to be about as simplified as we'll call this equation number 1 here is going to get. Okay, now what I want you to notice here is because it's a rectangle rather, and because the diagonal of a rectangle cuts it into 2 right triangles, we can apply the Pythagorean theorem here, right? So if we say that this is the length of the tile, And if we say that this is the width of the tile, well, and we know that this is the diagonal, right, from this pink dot here to this pink dot up there, well, what we know is that the length squared plus the width squared has to equal the diagonal squared, and of course, in this case, that's 100. Okay, let's kind of, for the moment, just call this equation 2. At this point, you know, a lot of even good students have the tendency to start doing some stuff that goes a little funky, okay, and for good reason. It seems like we're close to a solution, but it's tough to manipulate the equations we have here without being a little bit creative. Let me show you one interesting way we can apply some quadratics here. What we can do is we can actually square equation 1. I want you to watch me do this carefully so you can write it down and learn to see this in the future. So if we take this equation 1 here, watch what happens if we square the whole thing. So in other words, if we square this side and we square this side, well, some of you are saying, aha, that's one of our quadratic identities, right? So the quantity L plus W squared is the same thing as L plus W times L plus W, and 140 squared is, so 14 squared is 196, so 196,000. Okay, and we can take it a step further, guys. We can FOIL the L plus W's, right? And we're going to get L squared plus 2LW plus W squared, of course, is equal to 19,600. Okay, sorry guys for that noise. I have 2 rescue dogs who are telling me it's time for their dinner, so we'll have to feed them a little bit. Okay, so why did we do that? What was the point of going through that? Well, before I tell you, take a look at this finalized form here and take a look at equation 2. And I want you to sort of ask yourself, why did we do that? What can be done now with these 2 equations that will yield exactly what we're looking for? Okay? And what we're going to do, if you can see this, is we're going to take this guy here, and what we're going to do is we're going to subtract the equation 2 in pink, meaning we're going to subtract the entire thing. I'm going to stretch it out a little bit so you guys can better see why we're doing this. But what's happening here when we subtract this whole thing is, notice we're losing the L squareds and the W squareds, and quite cleverly we're left with 2LW is equal to 9,600. Divide both sides by 2, and we have LW is equal to 4,800. Of course, LW is length times width, another way of saying area. Okay, so if we go back to the question, it's asking us what's the area of the tile. Well, you know, you say tomato, I say tomato. You ask me for the area. I'll give you L times W is 4,800. Okay, and that's the answer to the problem. Now, I totally want you to see the quadratics in use here. And at the same time, I also want you to pay attention to this. This is a little bit of a side note that I think would be really valuable to all of you. You know, there's many ways to express the same thing in math. So we were asked for the area, but if we could just solve for LW, why not? That's the area too. Right? The formula doesn't have to, we don't have to come up with a formula that says, you know, area equals, right? This may be elementary to some of you, it may be revolutionary to others. Area is the same thing as like length times width. So we're able to effectively use the quadratic equation here to make this problem much simpler than it would be if you employed some more sort of traditional methods. So yeah, that's a good one. Jeff, how are we doing? We have time for one more problem? He's probably helping someone. Let's do one more problem here, guys, before we take some question and answers. I'm going to pick.
Yeah, Scott, we can do one more at least.
Okay, great. Let's do a challenging one here. This one's challenging because it's going to integrate multiple things you're going to have to do. There's multiple things in this problem that are trying to defeat you. I want you to use your creativity, and remember, don't ever start trying to make things complex or multiply lots of big numbers. Why don't we start the time now? Okay, guys, a little over 2 minutes. And so, you know, like this is difficult. So if you are not finished, obviously you would never get 37 questions of this difficulty. But what's interesting is you're going to see it's not really that difficult. And if you can take away anything from this webinar, the webinars that follow, is that the test is pretty darn doable once you're on the right track. And I'm going to just keep this really short, otherwise I get really sidetracked. I feel like there's so much disinformation and there's so much nonsense about how to solve problems and how to do this and how to do that. At the end of the day, I feel like the people who write the test must be laughing at all this information out there. Some of it's very good, don't get me wrong, but some of the strategies and the tactics are just a little bit off. Everything has a simple solution, a simple base to it. So some of you see this already, that we have the difference of squares in the numerator, right? 3 to the 30 minus 2 to the 30. Well, this can be re-expressed as 3 to the 15th squared minus 2 to the 15th squared. Okay, and that's still over this guy here. Well, there you go. There's your a squared minus b squared, or your x squared minus y squared, whatever you want to call it. But we have the difference of squares. And as soon as you see that, you can re-express the numerator, right? We can say this is 3 to the 15th plus 2 to the 15th times 3 to the 15th minus 2 to the 15th. And again, of course, the denominator was was instructive because it sort of has to leave, right? Like, where did it go? There's no equation. There's nothing else magical going on. The denominator had to leave because the answers are in the form of integers, right? And of course, at this point, you all see, well, this term can cancel off with this, and we're left with 3 to the 15th plus 2 to the 15th. And on an easier problem, perhaps that would actually be the answer. But we're faced with another challenge. We actually have to come up with one of these answer choices. Now, there's a couple strategies, but those of you who've had me or Jeff, you know, we harp a lot on unit digits because using unit digits or the one digit in a number is a pretty creative way to tag a number that you would otherwise, you know, need an Excel sheet or, you know, MATLAB or something to figure out. So what can we do here? Well, we're going to have to employ some number properties, and this will give us another chance to look at some other interesting patterns unexpectedly. So 3 to the 15th. Well, let's think about the units digit of powers of 3, and we'll do it over here on the left, right? So let's say we have 3 to the 1. Well, 3 to the 1 ends in a 3 unit digit of 3. 3 squared is a 9, a unit digit of 9. 3 cubed is 27, a unit digit of 7. And 3 to the 4th, I think, is 24, or 1, or something really close. But it ends in a 1. And what's interesting, guys, if you've never been exposed to this, sometimes it's a little bit revolutionary, is when you keep going higher and higher powers of 3, this pattern will continue. So the pattern will always be 3, 9, 7, 1, right? 3, 9, 7, 1, 3, 9, 7, 1. Okay, all the way into infinity. Okay, now this is a little tricky sometimes, but if you think about it, what it means is exponents that are power of 4, any power of 4, are going to have a unit digit of 1, okay? And so let's think about 3 to the 15. Well, what I like to say is, okay, well, what's the closest power of 4? Well, it's 3 to the 16, right? So as we just said, multiples of 4, exponents that are multiples of 4, are going to have a unit digit of 1, right? So this is a unit digit of 1. So therefore, 3 to the 15, all I have to do is go back 1 in the pattern, and we see that 3 to the 15 has a unit digit of 7. Okay, and sometimes students need more work than that. That's a good solution, sort of in a webinar format. You can obviously dig deeper into number properties and remainders if you need to. And we can do the same thing with 2 to the 15. So let's look at sort of what happens when we raise 2 to higher and higher powers. Well, 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 4th is 16. Unit digit of 6. And what's going to happen, guys, if we took the time to keep going higher and higher, we would see that powers of 2 always follow 2, 4, 8, 6. 2, 4, 8, 6, 2, 4, 8, 6, right, all the way up into infinity. Okay? So it's the same deal here. What we know is that powers of 2 that are, exponents of 2 that are powers of 4 have this unit digit of 6. Right? So what I would say to myself is I would say, well, what's the closest power to 2 to the 15? Well, 2 to the 16, that's a power of 4. Okay, so that must have a unit digit of 6. Therefore, 2 to the 15, well, that must be 1 back in the pattern. So 2 to the 15 must have a unit digit of 8. Okay, it must have a unit digit of 8. So now we're almost home, right? Because if you think about it, if some number has a unit digit of 7, and then we add it to another number that has a unit digit of 8, well, we produce a number that has a unit digit of 5. Okay, and if we look up at our answer choices, we see, through no mistake, that only one of these answer choices has a unit digit of 5. So deduction would tell us that that has to be the answer because we know there has to be one answer here. Okay, now this was a little complex of a problem, especially if you haven't seen or you're struggling with remainders. But those are definitely some patterns that are worth investigating. Okay, we could do probably another 200 problems here, and I think you'd benefit from every one of them. Just to be respectful of your time, I'm going to turn the floor back over to Jeff, and if you have any particular questions, I'm sure he could be more than willing to go over them with you, and you can always email me if you have any questions after the fact.
Yeah, everyone. So we have about 10 minutes. Feel free, if you have questions, to punch them into the chat box. One thing I was going to mention as I was looking at this question, something else you can kind of take away from here as a kind of a quick hit is that if you ever get to a question on the GMAT and you see the answer choices are in very high values, as Scott kind of mentioned tonight, making things easy on yourself, you know the GMAT's never going to force you to do values of that size. So if you look at the units digits of each answer choice here and you notice they're all different, chances are this is going to be able to be solved in some way using your unit digit patterns. So with that said, we are here to field questions if anyone has any, and if no one does, we can, do a few more questions to wrap up. I'll give you guys a minute to type anything in. I guess the better question I have for all of you is, would you rather see a few more questions? Okay, so we got that. Do we have a ditto on do more questions? Okay, so I see, okay, everyone wants to do questions. To reiterate, Scott and I, you can easily reach us, Scott at Target Test Prep, Jeff at Target Test Prep. If you want to talk more GMAT with us, we're always here. So Scott, let's do some more. And certainly, guys, I've been answering questions all night, so keep directing things to me if you have questions about what we're doing.
Okay. Okay, sounds good. Sounds good. Let me find an interesting one here that may deviate a little bit from some of the stuff that we've already done here so far tonight. Let's see. Okay, this is a really interesting one. I think you guys would benefit from seeing. So the beauty of this problem that I'm going to show you is it's going to ask you to look at, you can probably look at that and see it's some type of quadratic equation, but it's going to ask you to look at it in a different light, and it's going to ask you to connect some ideas that may be dissimilar in your mind at the moment, but we'll connect those. Excuse me. Why don't you give the guys this a whirl? We'll start now. All right, guys, that's about 2 minutes. And before we solve this, one thing you guys can do if you're planning to come back next Tuesday, Jeff told you we're going to do this regularly on Tuesday nights for a while. If you plan on coming back, it'd be great to get an email from you, just letting me know, just briefly, you know, where do these problems rank in difficulty from 1 to 10. If these were a 10 for everyone and people are coming back, we could make the problems a little easier. You know, if these problems are like a 2 out of 10 and you're coming back, we can make them a little bit harder. There's no reason why we can't try and personalize this a bit for people. Okay, so think about this. You know, for how many integers R is this number in this weird form going to be negative? So what hopefully you guys can see is that even though there's not an equal sign there, I mean, we're kind of all used to seeing the equal sign with structures like this, but even though there's not one there, we can still come up with the roots of the equation, right? We can factor it down. And the way to factor it down is just to say, okay, we need, you know, 2 terms that multiply to r to the 4th, so that's r squared. And you know, this 80 is positive here, so we know that, no, the 80 is positive, and excuse me, the center term is negative here, so we know we're going to have negative and negative, right, so that the 80 works out to be positive. And then we're just going to be, it's like solving like a jigsaw puzzle, right? What numbers will work here? Well, the numbers are 80 and 1. You can see that that multiplies to 80, and if you do the math through, it'll still get you 81r squared. Okay, now I want you to think about this. Here's where it sort of gets interesting. I'll give you a fresh perspective on some stuff you may not have thought about. Well, how can this be negative? How can the multiplication of 2 parentheses yield a negative number? Well, only way that's going to happen is if one of those parentheses is positive and one of those parentheses is negative, right? Because that's the only way we're getting a negative number out of this deal. Okay, so again, looking for simplicity. You can make it wildly complex, right, and debate about all these crazy methods. At the end of the day, it's not worth it. Okay, right, opposite signs, so positive and negative. Now, if you think about it, if one of these numbers has to be positive and one of these numbers has to be negative, well, which one has to be negative? And that's a really important exercise to see as well. Well, let's just call r squared a constant, right? Because it exists in both parentheses. So that's not going to change anything. So then really the chunk we have to think about here is the minus 80 in that one and the minus 1 in this one, right? So how does that help us? Well, if r squared is going to be a positive constant here because it's squared, well, doesn't the smaller number have to be negative? Let me say that again. If you have 2 parentheses being multiplied and we know one is negative and one is positive, doesn't the smaller number have to be sort of by definition the negative number? It does, right? And some positive constant in yellow, minus 80, is sure as heck smaller than the same positive constant minus 1. So we know the r squared minus 80 parenthesis has to be negative, and the r squared minus 1 parenthesis has to be positive. Okay? So it's all logic. The test is all about logic. Notice we're really not doing any heavy math here. We're really thinking a lot more than we're sort of busting through equations and processes, right? Okay, so if the r squared minus 80 is negative, well, let's call it what it is. If it's negative, by definition, it means that it must be less than 0. So let's just say how it is, less than 0. Okay, and if r squared minus 1 is positive, well, let's just call it what it is. It's greater than 0. That's a definition of a positive number. Okay, so let's start on the left here. So we'll add 80 to both sides. we see that r squared is less than 80, and we see that r squared is greater than 1. Okay, so what I like to do and what you may find helpful is just to make a compound inequality. What's that? Well, if r squared is less than 80, let's just say it, r squared is less than 80. And if it's greater than 1, let's say that too. So here is our compound inequality that shows you pretty nicely graphically, you know, where does r squared sit between these two. And now it's pretty easy as long as we're careful, right? So values of r have to make this little compound inequality true. Now, even the best of us sometimes do this. I've done it before. Students have done it before. We do this. We say, okay, well, r could be 2, right? Because 2 squared is 4, which fits in this inequality. They say r could be 3, because 3 squared is 9. That fits within the inequality. We say r could be 4, right, because 4 squared is 16, and that fits in the inequality. They say it could be 5, because 5 squared is 25, which fits inside of that inequality. We say it could be 6, because 6 squared is 36, fits in there, right? We say it could be 7, because 7 squared is 49, and it fits in there. Say it could be 8, right, plus 8, because that's what, 64, that fits in there. And we can't use 9, right, because 9 squared would be 81, which would be outside of the boundaries of this inequality. And in the haste of the test, we see, okay, that's 1, 2, 3, 4, 5, 6, 7. We say, okay, that's 7 values of r. We go up, we choose answer choice A. Of course, we got it wrong. Now take a minute and ask yourself why. Why did we get it wrong if we chose A? Okay, and the reason why we got it wrong if we chose A is you have to remember that these guys in their negative state, when they're squared, would also produce something that fits in between these two numbers. Okay, which makes it a little bit tricky, giving us a total of 14 different values. So obviously A is not the right answer. Okay, so interesting problem, okay, but again, you know, I've been saying this a lot, and I'll say it a lot as we go over the weeks here. You got to look for the simplicity. Notice all we did is employ a bunch of basic rules. Like you could argue that, and guys, I'm not taking away of the difficulty of the GMAT. Like we can look at the statistics and we know it's tough, but like I don't think we can argue that any of this stuff is higher than, you know, middle school or high school stuff. And the reason why I tell you that is if you can think about it directly and in a simplistic fashion, you're going to be so much farther ahead of the curve. Okay, so we can give the floor back to Jeff. We can still stay a little bit later if anyone has any questions for him. That'll probably conclude the problems I can kind of spit up off the top of my head here for you, but I hope to see you guys back next week, and email me if you have any questions. And if you have any questions now, certainly you can direct them to Jeff.
Yeah, thank you everyone for coming. I think we definitely covered a lot of ground. Does anyone have any general questions? And if not, yeah, we definitely look forward to everyone coming. I'm going to paste in a let me send it to everyone, a feedback kind of survey for everyone to fill out so we can start getting your feedback. Obviously, we want to make these webinars as impactful as we possibly can. So definitely fill those out. Everyone here is on the list. Everyone here will get a follow-up email with a discount code for our curriculum, and as Scott mentioned, we are always around if you want to email questions or have questions or want to chat and get on the phone. All of that is totally possible. So thanks again, and we'll see everyone next week.
Yeah, guys, Jeff made a really good point, especially if you're coming back. Fill out the feedback form carefully because you may as well get as much out of this as possible. If 30 people say the problem's too easy, we're going to make them more difficult. If 30 people say the problems were too difficult, we'll make them easy. So that'll be your opportunity to direct these webinars more towards your individual needs, which obviously is never going to be as good as one-on-one tutoring, but hey, you know what, let's try and get as close as we can. So thanks a lot, guys, for coming, and I hope you got some value out of this.